Time flows forward, 1 second per second. Past behind you, future ahead of you, present right here, right now, simple, obvious, undeniable. Except it's completely wrong. Not a little wrong. Not approximately wrong. Fundamentally, catastrophically, beautifully wrong. And Richard Feynman, one of the greatest physicists who ever lived, spent his career proving it. Here's what Feynman discovered. Time doesn't flow. There's no river of time carrying you from past to future. There's no universal clock ticking away somewhere in the cosmos. Time isn't even the same for everyone. Two people can experience different amounts of time doing the exact same thing. One person ages faster than the other. Their clocks disagree. Their realities diverge. And this isn't philosophy. This isn't metaphor. This is measured, tested, proven fact. Your brain cannot accept this. It refuses. Every fiber of your intuition screams that time is simple, that it flows the same for everyone, that now means now everywhere simultaneously. But that intuition evolved to help you catch prey and avoid predators on an African savanna. It was never designed to understand the actual structure of reality. And reality doesn't care what your brain was designed for. Let me show you something Feynman loved to demonstrate. Imagine two identical clocks, perfect atomic clocks, accurate to billionths of a second. You synchronize them exactly. Same time, same tick, same everything. Now, leave one on the ground. Put the other on an airplane. Fly the airplane around the world. Bring it back. Compare the clocks. They're different. Not broken. Different. The clock on the airplane experienced less time than the clock on the ground. Actual, real, measurable, less time. This actually happened. In 1971, physicists Joseph Hafele and Richard Keating took 4 atomic clocks on commercial airline flights around the world. When they returned and compared them to identical clocks that stayed on the ground, the traveling clocks had lost nanoseconds. Tiny amounts, but measurable, predictable, exactly matching Einstein's predictions that Feynman would later help refine and explain. Your brain wants to say the clocks malfunctioned. They didn't. Your brain wants to say something interfered with them. Nothing did. The clocks measured time accurately. Time itself was different. The airplane clock experienced less time because time passes at different rates depending on how fast you're moving. Feynman didn't just accept this. He worked out why. He showed that time and space are connected, woven together into a single fabric. And when you move through space, you change how you move through time. The faster you go through space, the slower you go through time. This isn't a side effect. This isn't a glitch. This is how time fundamentally works. Here's where it gets stranger. Feynman proved that there's no such thing as now, not in the way you think. When you say something is happening now, you mean it's simultaneous with you reading this. It's happening at the same time. But in physics, simultaneity doesn't exist. Two events that are simultaneous for you are not simultaneous for someone moving relative to you. They literally disagree about what happened first. Let me make this concrete. Imagine you're standing still and you see 2 lightning bolts strike at the exact same instant. One to your left, one to your right, equidistant from you. The light from both reaches your eyes at the same time. They were simultaneous. But now imagine your friend is on a train moving to the right. From their perspective, the lightning on the right struck first. Not because the light took different amounts of time to reach them, because, in their frame of reference, it actually did strike first. There is no universal agreement about what happened when. Feynman emphasized this again and again in his lectures. He'd draw space-time diagrams showing how events that appear simultaneous in one reference frame are separated in time in another. He'd explain how each observer carries their own version of now, their own slice through space-time. And these slices don't align. There is no master clock. There is no universal present moment shared by everyone. Each of us experiences our own timeline. This demolishes common sense. Your brain evolved to assume that if something is happening now on Earth, it's also happening now on Mars, now in another galaxy, now everywhere. That assumption is false. There is no synchronized cosmic instant. When you say, right now on a planet orbiting Alpha Centauri, that statement has no objective meaning. Different observers would disagree wildly about what moment you're referring to. Here's what Feynman taught his students. Stop thinking of time as a river you're floating down. Stop thinking of yourself as moving from past to future. Instead, imagine space-time as a four-dimensional structure, a block where past, present, and future all exist together. You're not moving through it. You exist as a four-dimensional object, a world line threading through space-time from birth to death. All moments of your life exist simultaneously in this structure. You just experience them one at a time. Your brain hates this. It insists you're in the present, that the past is gone, that the future hasn't happened yet. But physics says otherwise. Feynman showed that past, present, and future are distinctions we make, not features of reality. The equations don't care about now. They work the same backward and forward. Time symmetry, Feynman called it. The laws of physics don't distinguish between past and future in the way your brain does. Now watch this. Feynman didn't just study time. He revolutionized how we understand it through quantum mechanics. And in quantum mechanics, time gets even stranger. Particles don't follow single paths through space-time. They follow all possible paths simultaneously. Feynman developed a mathematical framework called path integrals to describe this. A particle going from point A to point B doesn't take one route. It takes every route, every possible trajectory through space and time, all at once. Here's what that means. When a photon travels from a light source to your eye, it doesn't just go straight. It goes every possible way. It bounces off Mars. It loops around the moon. It zigzags through space. Every conceivable path contributes to where the photon ends up. Feynman showed you calculate the probability of detection by adding up all these paths, giving each a certain weight based on the action along that path. The result matches experiment perfectly. This isn't metaphor. This is the actual mathematical description of reality. Particles explore all paths through space-time. They don't choose one, they take all of them. Your brain cannot visualize this. Don't try. The math works. The predictions match observation. That's what matters. But here's where Feynman dropped the real bomb. In quantum mechanics, time doesn't have to go forward. In his path integral formulation, particles can move backward in time, not a speculation. As part of the mathematics, a positron, the antimatter version of an electron, is mathematically identical to an electron moving backward through time. Feynman and his colleague John Wheeler seriously proposed this. Every positron in the universe might be the same electron zigzagging back and forth through time. Think about what this means. An electron moves forward in time, interacts with something, reverses direction, and moves backward in time. As a positron, interacts again, reverses again, forward as an electron, backward as a positron, over and over. One particle threading through space-time, creating the appearance of many particles. Feynman eventually backed away from this specific idea, but the mathematics remained. Time reversal is baked into quantum field theory. Your intuition screams that this is impossible. Things age. Entropy increases. Eggs don't unbreak. Coffee doesn't spontaneously separate from cream. Time has an arrow. It points forward. But Feynman showed that the fundamental laws of physics are time-symmetric. The arrow of time, The direction that distinguishes past from future doesn't come from the laws themselves. It comes from statistics, from the fact that there are many more disordered states than ordered states. Entropy increases because disorder is more probable, not because time inherently flows forward. Let me say that again because it's crucial. The equations governing particles don't care about time direction. An electron interacting with a photon works the same backward as forward. The reason you see time flowing forward, the reason eggs break but don't unbreak, is statistical. It's overwhelmingly unlikely for entropy to decrease, for randomness to spontaneously organize. But it's not forbidden by fundamental physics. Time's arrow is emergent, not fundamental. Feynman loved pointing this out in his lectures at Caltech. He'd run film backward, showing waves converging on a beach instead of spreading out, and he'd ask students to spot what was wrong. The answer: nothing is fundamentally wrong. The laws of physics permit the reversed motion. It's just statistically unlikely. The ocean molecules could, in principle, arrange themselves to create that converging wave. They just never will, because the odds are astronomically against it. Here's another thing your brain gets wrong about time. You think you remember the past and predict the future. That seems obvious. Memory stores what happened. Prediction guesses what will happen. But Feynman showed that in physics the distinction isn't so clear. Information about the future can affect the present just as much as information about the past. In quantum mechanics, this is called retrocausality. Under certain interpretations, the state of a system can depend on measurements that haven't been performed yet. Feynman's absorber theory of radiation, developed with Wheeler, suggested that light waves traveling backward in time from future absorbers help determine the behavior of emitters in the present. The theory didn't become mainstream, but it illustrated something profound. Our intuition about cause and effect, about past influencing future, but not vice versa, might be too simplistic. Every delayed choice quantum eraser experiment confirms this weirdness. You can perform a measurement now that retroactively determines what happened in the past. Not changes the past, determines what kind of past occurred. The future measurement affects which history actually happened. Feynman's framework explains this naturally. In path integrals, all paths through spacetime contribute, including paths that loop through time in complicated ways. Causality isn't a simple forward chain. Now let me tell you what Feynman said about understanding time. He was famous for his honesty, for admitting when he didn't understand something. And he said repeatedly, nobody understands time. Not him, not Einstein, not anyone. We have equations that work. We make predictions that match experiments. But do we truly understand what time is? No. In his book, The Character of Physical Law, Feynman wrote that we can describe how time behaves in our theories, but we can't say what time actually is. We measure it, we observe its effects, we incorporate it into mathematics. But we don't have intuition for it. We don't grasp it the way we grasp space or matter. Time remains mysterious at a fundamental level. Here's why your brain fails at time. Your brain constructs a model of reality based on sensory input. That model includes time as a smooth, universal flow. Events happen in sequence. Cause precedes effect. Now means now for everyone. This model works brilliantly for survival. It lets you catch a ball, plan your day, remember where you left your keys. But it's a simplified cartoon of actual time. Actual time is relative. It dilates with speed and gravity. It has no universal present. Its direction emerges statistically rather than fundamentally. It might not even be continuous at the smallest scales. Quantum gravity theories suggest time could be quantized, broken into discrete chunks smaller than anything we can measure. Time might not exist at all at the Planck scale, the smallest possible length scale in physics. Feynman knew this. He worked on quantum gravity. He understood that our current theories of time break down at extreme scales. General relativity describes time as part of curved spacetime. Quantum mechanics describes time as a parameter in wave function evolution. These descriptions are incompatible. We don't have a unified theory of quantum gravity that explains what time is when both quantum effects and gravitational effects matter. Time remains a mystery. But here's what we do know, what Feynman helped prove beyond doubt. Time is not what you think it is. It's not a universal river. It's not the same for everyone. It doesn't flow at a constant rate. The past, present, and future don't exist in the way your brain insists they do. Simultaneous is relative. Time's arrow is statistical. And at the quantum level, particles don't even experience time the way you do. Let me give you one more example of how strange time really is. Feynman worked extensively on quantum electrodynamics. QED, the theory of how light and matter interact. In QED, when you calculate the probability of an event, you sum over all possible ways it can happen. And some of those ways involve particles traveling backward in time, virtual particles popping in and out of existence, interactions happening in scrambled temporal order. These aren't real particles in the sense of things you can detect. They're mathematical tools, but they're necessary mathematical tools. The calculations only work when you include these time-reversed, causally scrambled processes. Feynman diagrams, the visual representations he invented, show particles moving both forward and backward in time. To get the right answer, to match what experiments measure, you have to add up all these diagrams, including the temporally weird ones. What does this tell us? That our intuitive notion of time as a simple forward progression is inadequate for describing reality. The universe doesn't care about our intuitions. The universe operates according to rules that permit time reversal, that treat past and future symmetrically, that allow quantum systems to explore all temporal possibilities simultaneously. Feynman embraced this. He didn't try to make quantum mechanics fit common sense. He followed the mathematics wherever it led, and it led to a picture of time that is alien to human intuition, but extraordinarily accurate in its predictions. QED is the most precisely tested theory in the history of science. Its predictions match measurements to 10 decimal places, and it achieves this precision by treating time in ways your brain finds absurd. Here's the deepest point. Time might not be a fundamental feature of the universe at all. It might be emergent, arising from something more basic. Some theories of quantum gravity suggest that space-time itself, including time, emerges from quantum entanglement, from correlations between quantum states. At the most fundamental level, there might be no time, no space, just quantum information arranged in certain patterns. Time is what we experience when we observe the universe from within, but it's not part of the universe's deepest description. Feynman didn't live to see these theories develop fully, but he anticipated them. He knew that time was stranger than it appeared. He knew that our current understanding was incomplete. And he knew that the next revolution in physics would likely involve a radical reconception of what time is. So what does this mean for you? It means the flow of time you feel. The progression from past through present to future is a construction of your brain. It's not an illusion exactly. You do experience it. But it's not a feature of fundamental reality. It's an emergent phenomenon, arising from the way macroscopic systems like brains process information and interact with their environment. Different observers, moving at different speeds or in different gravitational fields, experience time differently. There is no privileged perspective, no correct rate of time flow. Each observer has their own valid timeline, and these timelines don't align in the way you'd expect. Feynman proved this through his work on relativity and quantum field theory. The mathematics is unambiguous. Let me address something that might be bothering you. If time doesn't flow, if past and future exist equally, what about free will? What about choice? If all moments exist in a space-time block, is everything predetermined? Feynman addressed this, though not definitively. He pointed out that quantum mechanics introduces genuine randomness. Particle behaviors are probabilistic, not deterministic. You cannot predict with certainty what a quantum system will do. This randomness might provide room for free will, or it might not. Feynman didn't claim to have the answer. He emphasized that the question involves philosophy as much as physics. What he did insist on is this: whatever free will is, it has to be compatible with the actual physics of time. It can't rely on a flowing river of time that doesn't exist. It can't assume a universal present that isn't real. If we have free will, it operates within a space-time structure, where past, present, and future all exist, where time is relative, where quantum probabilities govern outcomes. Our choices, if they're real, are part of that structure, not exceptions to it. Here's what Feynman wanted people to understand. Physics doesn't tell you what to believe about consciousness or free will, or the meaning of existence. Physics tells you what the universe does, how it behaves, what rules it follows. And those rules say time is far stranger than common sense suggests. Your job isn't to make physics fit your intuitions. Your job is to update your intuitions based on what physics reveals. The universe is under no obligation to make sense to a primate brain that evolved to throw rocks and find berries. The fact that we can understand anything about the deep structure of reality is remarkable, but understanding requires us to abandon our intuitive pictures and accept what the mathematics and experiments tell us. Time doesn't flow. Now is not universal. Past and future are not fundamentally different. Particles can move backward in time in quantum field theory. Time might not even be fundamental. These aren't opinions. These are conclusions forced on us by overwhelming evidence. Feynman spent his life studying time, and he concluded that nobody really understands it. We have excellent mathematical descriptions. We can predict time dilation to extraordinary precision. We can calculate quantum processes involving temporally complex paths. But do we understand what time fundamentally is? No, we don't. And maybe we never will. Maybe time is too far outside our evolutionary experience for us to ever develop true intuition for it. Maybe the best we can do is mathematics, equations that work even though we can't visualize what they describe. But here's the beautiful part. We don't need intuition to do physics. We need careful observation, rigorous mathematics, and willingness to accept uncomfortable conclusions. Feynman exemplified this. He didn't pretend to understand things he didn't. He didn't force reality to fit comfortable categories. He followed the evidence. And the evidence says your brain was never meant to understand time, because time is nothing like what your brain assumes. I know this is deeply unsatisfying. You want a simple answer. You want time to make sense. But demanding that reality conform to your expectations is backwards. Reality is what it is. Time is what it is. And what it is, according to our best physics, according to Feynman's lifetime of work, is something profoundly alien to human intuition. Two clocks, one on the ground, one on a plane, experience different amounts of time. That's real. Two observers disagree about whether events are simultaneous. That's real. Particles in quantum field theory take paths that move backward through time. That's real. The past, present, and future exist equally in space-time. That's real. Or at least it's the picture that emerges from general relativity. Your brain rejects this. That's fine. Your brain isn't equipped to accept it. But the mathematics doesn't care. The experiments don't care. Time continues to behave exactly as relativity and quantum mechanics predict, regardless of whether your intuition approves. Feynman proved that understanding physics means accepting you won't understand physics the way you understand everyday objects. You won't develop common sense about time dilation, or quantum superposition, or space-time curvature. You'll develop mathematical fluency. You'll learn to calculate, to predict, to test. But the gut-level feeling of understanding, the intuitive grasp, that's not available for most of physics. And that's okay. That's not a failure. That's the nature of the universe. We're pattern-matching animals trying to comprehend a cosmos that operates on principles entirely foreign to our ancestral environment. The miracle isn't that we find it difficult. The miracle is that we succeed at all. We can't visualize four-dimensional space-time. We can't intuitively grasp quantum superposition. We can't feel what it's like for time to pass at different rates, but we can describe these phenomena mathematically. We can test the predictions. We can build technologies that rely on these strange truths, like GPS satellites that must account for relativistic time dilation to function accurately. Every time you use GPS, you're relying on corrections for the fact that time passes differently for satellites in orbit than for receivers on the ground. The system wouldn't work without accounting for general and special relativistic effects on time. Your phone proves Feynman right every time you navigate. So here's where we are. Time is not a universal flow. It's relative, malleable, possibly emergent, definitely weird. Different observers experience it differently. Quantum mechanics allows time-reversed processes. The arrow of time is statistical, not fundamental, and at the deepest level, time might not exist at all in the way we experience it. Feynman knew all this. He helped discover much of it. He spent decades teaching it, explaining it, emphasizing how strange it is. And his conclusion was honest and humbling. We don't really understand time. We can describe it mathematically. We can make astonishingly accurate predictions. But true understanding, the kind where it makes intuitive sense, eludes us. Your brain was never meant to understand time, because time is not what evolution prepared you for. Time, as it actually exists according to physics, is a four-dimensional component of space-time, relative to observers, symmetric under reversal in fundamental equations, emergent from quantum correlations, possibly not fundamental at all. That's the truth Feynman proved, not through a single experiment, but through a lifetime of work in quantum mechanics, quantum electrodynamics, and quantum field theory. He showed that time is far stranger than anyone imagined, that our intuitions are not just incomplete, but actively misleading. And yet, we figured it out. Creatures who evolved to track prey and gather food developed mathematics sophisticated enough to describe the true nature of time. We can't feel it in our bones. We can't visualize it in our minds. But we can write down equations that capture it, run experiments that confirm it, build technologies that exploit it. That's the power of physics, not making things intuitive, but making them precise. Not confirming what we already believe, but revealing what's actually true. And what's actually true about time is that your brain was never meant to understand it. But you can still learn about it. You can study the equations, examine the evidence, accept the conclusions. You can know, even if you can't intuitively grasp, that time is relative, that simultaneity is observer-dependent, that past and future are not fundamentally distinct. Feynman proved it. The experiments confirm it. And every GPS satellite, every particle accelerator, every atomic clock, every test of relativity adds more evidence. Time is not what you think. It's stranger, more subtle, more fundamental, and yet possibly less real than your brain insists. That's the final lesson. The universe doesn't owe you comfort. It doesn't owe you intuitive clarity. It just is. And what it is far more interesting than what you imagined. Your brain was never meant to understand time. But thanks to Feynman and physicists like him, You can know the truth about it anyway, even if that truth feels impossible, even if it contradicts everything your intuition screams, even if it means accepting that the flow of time, the most obvious feature of your existence, is not a feature of the universe at all. That's physics. That's reality. That's what Feynman proved. And that's why time remains one of the deepest mysteries in science, even as we use it, measure it, and build our entire civilization around it.